All right, welcome to another deep dive. This time we're going to tackle aerospace engineering.
Oh, this is gonna be fun.
Yeah. You gave me a ton of articles and notes on this one.
I did.
So let's see if we can
Yeah.
distill it down
Uh-huh.
to the
Here's
essentials.
the good stuff.
Yeah, and see if we can pull out any of the hidden gems, the mind-blowing facts
Sounds good to me.
about how things fly, which is
Yeah.
still kind of blows my mind. We
Yeah.
figured this out.
It is kind of mind-blowing.
So maybe we should start with the basics, like
Right.
what even is aerospace engineering?
Well, at its core, aerospace engineering is about designing and building machines that fly.
Okay.
And not just planes, but also spacecraft.
Right, right. So anything that goes
Or
up.
anything that leaves the
So
ground.
does that mean aerospace engineering is basically rocket science?
Haha. Well, you could say that, but it's a lot more than just rockets.
Okay.
There are two main branches. Aeronautical engineering, which focuses on aircraft, and astronautical engineering, which deals with spacecraft.
So one's about staying within Earth's atmosphere,
Right.
and the other one is about like going beyond.
Exactly.
Okay, so that makes sense. I guess it all started with like the dream of flight.
It did. And those early pioneers had to figure out some pretty fundamental things, like
Yeah.
how do you generate enough lift to overcome gravity?
Yeah, that's a good question. Like, how did they even begin to figure that out?
Well, we have to go back centuries to find the roots. Back in the late 1700s and early 1800s,
Okay.
there was this guy named Sir George Cayley.
Okay.
He's often called the father of aeronautics.
I've heard that name before.
Yeah, he was one of the first to really understand the concept of lift
Okay.
and how it's distinct from drag, which
yeah.
those are the two fundamental forces that every flying machine has to deal with.
Gotcha. So he was like laying the groundwork.
Exactly. He was a visionary way ahead of his time.
Huh. So Kaylee figures out lift and drag, and then what happens?
Well, it takes a while for those ideas to turn into a real flying machine.
Right.
But then, in 1903, the Wright brothers make history with their famous 12-second flight at Kitty Hawk.
Oh, yeah. I remember learning about that in school. That must have been a huge moment.
It was a pivotal moment. They took Cayley's theories and turned them into reality.
Wow. 12 seconds that changed the world.
And it wasn't long before World War I broke out, which, as you can imagine,
Yeah.
the need for faster and more agile military aircraft really accelerated the development of aerospace engineering.
Wars tend to do that, don't they? Like push technology forward.
They do, for better or worse.
Yeah, true. So after World War I, what happened? Did things slow down?
Not at all. The period between the two world wars saw the rise of civil aviation.
Yep.
Planes like the Curtiss JN4 Jenny and the Ford Trimotor became iconic.
Those names sound familiar.
Yeah, they showed that air travel wasn't just a novelty anymore. It could be practical and reliable.
Oh, that's interesting. So while all this was happening with planes, was anyone thinking about space travel yet?
Oh, yeah. While the world was focused on planes, Robert Goddard was thinking about rockets.
Goddard, wasn't he like a...
He was a visionary.
Okay.
Way back in 1914, he received patents for ideas that would later be crucial for space travel.
Wow, 1914. That's early. What kind of ideas?
He had patents for liquid-fueled rockets.
Oh, wow.
And multi-stage rockets, things that would become essential for reaching space.
So he was basically laying the foundation for the space race.
He was, but then World War II happened, which also had a huge impact on aerospace engineering.
I bet. What kind of advancements came out of that?
Well, World War II led to the development of the first jet-powered plane, the Messerschmitt Me 262.
Oh, wow. Jet engines. That must have been a massive leap forward.
It was a game changer in terms of speed and power.
Okay, so we've got planes getting faster and more powerful.
Yeah.
But space travel still seems pretty far-fetched at this point, right?
It does, but that all changes in 1957
Okay.
when the Soviet Union launched Sputnik.
Sputnik, the first satellite.
The first artificial satellite to orbit Earth.
I can only imagine how that must have, like, shocked the world.
It did. It kicked off the space race and marked the beginning of the Cold War era in aerospace engineering.
Wow, so that little satellite really changed everything.
It did. The U.S. responded quickly by establishing NASA and
Yeah.
pouring resources into catching up.
And then, of course, we have the Apollo 11 moon landing in 1969.
One small step for man, a giant leap for mankind.
Exactly, a pivotal moment in human history. Okay, so before we get too lost in space,
Yeah.
we should talk about the Boeing 747.
The jumbo jet.
Yeah, that thing is iconic. How did that come about?
Well, the Boeing 747 entered commercial service in 1970.
Okay.
Its sheer size and passenger capacity revolutionized air travel, especially for long-haul flights.
Right, it made flying accessible to more people.
Exactly.
And then there's the Concorde, which, for a while, supersonic travel seemed like the future.
It did. The Concorde debuted in 1976 and was a marvel of engineering.
But it didn't really last, did it?
It faced a lot of challenges, high operating costs,
Yeah.
limited routes due to noise restrictions,
Mhm.
and of course, the tragic crash in 2000.
Yeah, that's true. It's a good reminder that even the most groundbreaking technology can't always overcome those real-world constraints.
Exactly. But those failures often lead to new innovations.
That's a good point. So we've talked about the history and some of the iconic planes,
Yeah.
but what about the science behind all of this? Like, what are some of the key elements that make up this field?
Well, aerospace engineering involves understanding a complex interplay of scientific principles.
Okay, like what?
Well, for instance, there's fluid mechanics, which is all about how air, a fluid, flows around objects like wings to generate lift.
Okay, so lift is obviously key to getting anything off the ground.
It is.
But how does the shape of a wing actually create lift?
That's a great question. And it's all about manipulating the airflow.
Mm.
Imagine you're throwing a ball horizontally. If you throw it with enough force, it won't just drop straight down, right?
Right, it'll travel forward while falling.
Exactly. And if you could throw it with enough force, it would essentially fall around the curvature of the Earth.
Whoa, okay, so that's like the basic idea behind an orbit.
It is. It's about balancing the forward motion with the pull of gravity.
Gotcha. So with a wing, it's the shape, what's it called? An airfoil?
Airfoil.
Okay, so the airfoil somehow manipulates the airflow to create that balance.
Exactly. The curved upper surface forces the air to travel a longer distance than the air flowing underneath.
All right.
According to Bernoulli's principle, faster moving air has lower pressure, so you get lower pressure above the wing
Yeah.
and higher pressure below.
So it's not just about air pushing up on the bottom of the wing, it's more about this pressure difference.
Precisely.
Yeah.
And that difference in pressure is what generates the upward force, the lift that counteracts gravity.
Okay, so there's a lot more to lift than I realized. What about astrodynamics? That sounds kind of intimidating.
It sounds fancy.
Yeah.
But it's basically celestial mechanics applied to spacecraft.
Okay, so like how to predict and control the paths of rockets and satellites.
Exactly. Imagine a spacecraft orbiting Earth.
Okay, picturing it.
It's constantly being pulled down by Earth's gravity, right?
Yeah.
But it's also moving forward with a certain velocity.
Okay.
To stay in orbit, you need to find that sweet spot where the spacecraft is moving fast enough that it constantly falls around the Earth instead of crashing back down.
So it's like that ball we were talking about, just on a much bigger scale.
Exactly. But space is a pretty complex place.
Right, there's a lot more going on up there.
There's atmospheric drag, which is friction from the thin upper layers of the atmosphere.
Okay.
And then you have the gravitational pull of other celestial bodies, like
Ah.
the moon and the sun.
So it gets pretty complicated.
It does. Astrodynamics involves some serious math and physics.
Yeah, that makes sense. Okay, so we've covered fluid mechanics, astrodynamics.
Mm-hmm.
What about propulsion? There are a lot of different ways to make things move.
We've talked about jet engines, which use air-breathing propulsion, but those won't work in the vacuum of space.
Yeah, no air up there to suck in.
Exactly.
So what do they use in space?
Rocket engines.
Okay, and those work how?
They operate on a different principle called rocket propulsion.
Okay.
They carry their own oxidizer, a chemical that allows combustion to occur even without air.
Oh, right, because combustion needs oxygen.
Exactly.
So they're bringing their own oxygen supply with them.
They are. A rocket engine combines fuel and oxidizer in a combustion chamber.
Yeah.
Creates a controlled explosion, and that expels hot gas out of a nozzle to produce thrust.
So they're basically harnessing the power of explosions to move through space.
In a very controlled way, of course.
Right, of course. Okay, so we've talked about how things fly and how they stay in orbit.
Yep.
But what about the materials they're made of? I know that planes and spacecraft need to be incredibly strong and lightweight.
You're absolutely right. Material science is a crucial part of aerospace engineering.
Okay, so what are some of the key considerations when choosing materials for these vehicles?
We'll take spacecraft, for example. They need materials that can handle extreme temperature swings.
Right, from the heat of the sun to the cold of deep space.
Exactly. And they need to withstand micrometeoroids and orbital debris.
What's that?
Tiny particles that can zip around at incredibly high speeds and cause damage.
Oh, wow.
And then there's radiation, which can degrade materials over time.
Yikes. So it's a pretty hostile environment up there.
It is. So we need materials that can handle all of that.
What kind of materials can actually do that?
Well, it depends on the specific application.
Okay.
For thermal management, you need materials with specific properties, like high reflectivity or good insulation.
Okay.
To protect against impacts, you might use layers of shielding made from materials like Kevlar or aluminum.
Gotcha.
And to mitigate radiation damage, you need radiation-hardened electronics.
And what about strength and weight? Didn't you say they need to be lightweight?
Oh, yeah, absolutely. For
Yeah.
that, we use materials with a high strength-to-weight ratio.
Okay, what are some examples?
Titanium alloys are often used for components that need to be both strong and lightweight.
Okay.
And composites, like carbon fiber reinforced polymers, are becoming increasingly popular.
Oh, yeah, I've heard about those. They're like super strong and super light, right?
They are. They're a real game changer in aerospace design.
So it sounds like material science is constantly evolving in this field.
It is. We're always searching for lighter, stronger, and more resilient materials.
All right, so we've talked about a lot of the science behind aerospace engineering, but there's one more thing I want to touch on before we wrap up this part of our deep dive.
Okay.
Flight testing. It's like the moment of truth, right? Where all those design and calculations are put to the test.
Exactly. Flight testing is an essential part of the development process.
All right, so what exactly does a flight test process look like?
Well, a typical flight test program usually has three main phases:
Okay.
preparation, execution, and analysis and reporting.
Okay, so break those down for me.
Well, the preparation phase involves defining the objectives of the tests, developing detailed test plans, and making sure the aircraft is instrumented to collect data.
So it's all about planning and getting ready for those test flights.
Exactly. Then comes the execution phase.
Okay, and that's where the test pilots come in.
Right. Highly skilled test pilots take the aircraft through a series of carefully designed maneuvers, pushing its limits to gather data.
Wow, that must be an incredible experience for the pilots.
It is. It requires a unique combination of skill, courage, and technical expertise.
And all the while, there's a team on the ground monitoring everything.
Absolutely. Engineers are on the ground monitoring the data streaming in real time.
Okay, making sure everything is going according to plan.
Exactly. And then comes the final phase, analysis and reporting.
So after the test flights, it's time to crunch the numbers.
Exactly. Engineers pore over the mountains of data collected, looking for anything that seems out of place.
Any anomalies.
Right. They want to identify any potential issues or areas for improvement in the aircraft's design.
Okay. And then they summarize their findings in detailed reports.
It's like a constant feedback loop.
It is. The data gathered during flight testing informs the design and engineering process.
Wow, so it's a very iterative process.
It is. It's a continuous cycle of testing, analyzing, and refining.
It's amazing to think about all the work and expertise that goes into every single flight we take.
It is. Aerospace engineering is a truly remarkable field.
I agree. So in this first part of our deep dive, we've explored the history of aerospace engineering.
From those early pioneers to the iconic aircraft that have changed the world,
We've even delved into some of the key scientific elements.
like fluid mechanics, astrodynamics, propulsion, and material science.
It's been an incredible journey so far. It has. Before we move on, I wanted to add one more thought about flight testing.
Okay.
It's not just about making sure things work.
Right.
It's also about pushing the boundaries of what's possible
Okay.
and learning from both successes and failures.
That's a good point. Innovation often comes from, taking risks and learning from those experiences.
Exactly.
I'm curious about some of the other, like, record-breaking aircraft that came after the Concorde.
Okay.
What about that Antonov An-225 Maria?
Oh, the Maria.
Yeah, I've heard it was like the heaviest aircraft ever built.
It was a behemoth. It first took flight in 1988
Okay.
and was designed to carry oversized cargo.
Like what kind of cargo?
Things like space shuttle components.
Wow, that's crazy. It's amazing that something that massive could even get off the ground.
It was a remarkable feat of engineering. Sadly, it was destroyed in 2022 during the conflict in Ukraine.
Oh, that's right. I remember hearing about that. It's a shame to lose such a unique aircraft.
It is.
Okay. And what about passenger capacity?
Okay.
I know the Airbus A380 is like in a league of its own, right?
It is. The A380 debuted in 2007 and
Right.
could carry over 850 passengers.
Wow, that's a lot of people.
It is. It's the largest passenger airliner in the world.
Wow, so it was designed for those like high volume air travel routes.
It was. But like the Concorde, it's faced some commercial challenges in recent years.
Interesting. It seems like there's always this push and pull between technological innovation and those economic realities in aerospace engineering.
There is.
Okay, so we talked about some of the scientific elements earlier,
Yeah.
but I'm hoping we can, unpack them a bit further.
Sure.
Let's start with fluid mechanics.
Okay.
I'm still a little fuzzy on how air flowing over a wing actually generates lift.
It's one of those things that seems counterintuitive at first
Yeah,
until you understand the physics behind it.
right.
We talked about Bernoulli's principle, which states that faster-moving air has lower pressure,
Okay.
and the shape of an airfoil is designed to exploit that principle.
Okay, so the airfoil makes the air move faster over the top surface of the wing,
Yeah.
but how does that translate into an upward force?
It's all about the pressure difference. Because the air is moving faster over the top of the wing, it has lower pressure compared to the slower moving air underneath.
Okay.
And that pressure difference creates an upward force, like a suction effect.
Pulling the wing upward.
Exactly.
So it's not just about air pushing up on the bottom of the wing, it's more about the pressure difference created by the way the air flows around the whole wing.
Precisely. And to get a bit more technical, the amount of lift generated also depends on the angle of attack.
Okay, and remind me what that is again.
The angle of attack is the angle between the wing and the oncoming airflow.
Okay.
Increasing the angle of attack can increase lift, but only up to a point.
So there's the sweet spot.
There is.
All right, I'm starting to see why they call it rocket science.
Haha.
Now, what about astrodynamics?
Okay.
You mentioned it's about predicting and controlling the paths of spacecraft.
Right.
Can you give me a little more detail on how that actually works?
Sure. Astrodynamics is all about applying the laws of physics, particularly Newton's law of universal gravitation, to celestial objects.
Okay.
Imagine you have a spacecraft orbiting Earth.
All right, I'm picturing it.
It's constantly being pulled towards Earth by gravity,
Right.
but it also has a certain velocity that keeps it moving
Or
forward.
that balancing act.
Exactly. If the spacecraft is moving too slowly, it'll fall back to Earth.
Okay.
But if it's moving too fast, it'll escape Earth's gravity and fly off into space.
So you got to find that Goldilocks zone.
You do. You need to find that perfect velocity that allows the spacecraft to continuously fall around the Earth without actually getting any closer to the surface.
So it's like it's constantly falling, but also constantly missing the Earth.
That's a great way to put it.
But space isn't exactly empty, is it?
It's not.
Are there other forces that astrodynamicists have to take into account when calculating these orbits?
Absolutely.
No.
There's atmospheric drag, which can gradually slow down a spacecraft
Okay.
and cause its orbit to decay over time.
So they have to adjust for that.
They do. And then there's the gravitational influence of other celestial bodies, like the moon and the sun.
Okay.
These can perturb a spacecraft's trajectory, especially for missions that venture beyond Earth's immediate neighborhood.
So it's a lot more complicated than just plotting a straight line from point A to point B.
It is. Astrodynamicists use sophisticated computer models to calculate these trajectories
Okay.
and make sure spacecraft stay on course.
So it's like a constant process of monitoring and adjusting.
It is.
All right, let's shift gears again and talk about propulsion.
Okay.
We talked about jet engines, which are amazing,
They are.
but they need air to work.
Yeah.
How do you create propulsion in the vacuum of space where there's no air?
That's where rocket engines come in.
Okay.
Unlike jet engines, rocket engines don't need air to operate because they carry their own oxidizer.
Right. Their own oxygen supply.
Exactly. The most common type of rocket engine uses liquid propellants,
Right.
a fuel, like liquid hydrogen, and an oxidizer, like liquid oxygen.
Okay. And how do those create thrust?
It all happens in the combustion chamber.
Oh.
The fuel and oxidizer are mixed and ignited,
Oh.
creating a controlled explosion.
Controlled explosion. That sounds a little dangerous.
It's very controlled. It produces hot, high-pressure gases,
Okay.
and those gases are expelled out of a nozzle at the bottom of the engine,
Okay.
and that creates thrust, pushing the rocket forward.
So it's like for every action, there's an equal and opposite reaction.
Exactly. It's Newton's third law in action.
The force of those gases pushing out the back pushes the rocket forward.
Precisely.
That's really cool. Okay, let's talk about material science again.
All right.
We talked about those challenges of finding materials that can withstand the extreme conditions of space.
Yeah.
But let's dig a little deeper into some of the specific properties that make those materials so special.
Sure. One of the most important properties is the strength-to-weight ratio.
Okay.
You want materials that are incredibly strong.
Right, to handle all those courses.
Exactly. But also lightweight to minimize the overall mass of the vehicle.
Right, because the heavier it is, the more fuel you need to get it off the ground or into
Yeah,
space.
Exactly.
So what kind of materials can actually achieve that combination of strength and lightness?
Some of the most commonly used materials include aluminum alloys,
Okay.
titanium alloys,
Hmm.
and composites like carbon fiber.
Okay, and each of those has its own, like, unique set of properties.
They do.
What makes aluminum so useful?
Aluminum is lightweight, relatively inexpensive, and easy to work with.
Okay.
It's often used for aircraft fuselage structures, wings, and fuel tanks.
Okay, what about titanium? When do they use that?
Titanium is even stronger and more heat-resistant than aluminum,
Okay.
so it's often used for engine components
Like it says,
or parts of the spacecraft that experience re-entry.
where things get really hot.
Very hot.
Okay, and what about those carbon fiber composites?
Composites. They offer an amazing combination of strength, stiffness, and lightness.
Yeah, they seem to be like the cutting edge.
They are. They're becoming increasingly popular, especially for aircraft wings and fuselage sections.
So it sounds like choosing the right material for each part of a plane or spacecraft is kind of a big deal.
It is. Engineers have to carefully consider the specific requirements of each component,
Okay.
the loads it will experience, the temperatures it will be exposed to, and any other environmental factors.
So it's like a giant jigsaw puzzle where each piece has to fit perfectly and be made of the right stuff.
That's a great analogy.
It really highlights how complex this all is.
It is. Aerospace engineering is a highly interdisciplinary field.
Okay, what does that mean?
It means you need expertise in many different areas.
Like what? Give me some examples.
Aerodynamics, propulsion, structures, materials science, avionics, the list goes on.
So it's not a field for people who like to specialize.
It can be, but a broad understanding is definitely helpful.
Okay, so even with the best materials and the most careful design,
All right.
things can still go wrong during flight.
Unfortunately, that's true.
That's why flight testing is so important, right?
Absolutely. Flight testing is all about evaluating the aircraft's performance and safety in a real-world environment.
Okay, so can you tell me a bit more about the specific types of tests they do?
Sure. One important set of tests focuses on the aircraft's handling qualities.
Okay, like what?
Test pilots put the aircraft through a series of maneuvers,
Okay.
evaluating its stability, controllability, and responsiveness to pilot inputs.
So they're making sure it handles well and does what it's supposed to. Well,
Exactly. They're checking things like how well it turns, how quickly it climbs, and how it handles in different weather conditions.
okay, what about performance testing?
Performance tests focus on things like speed, range, fuel efficiency, and climb rate.
Okay, so they're measuring how well it actually performs.
Exactly. Engineers want to verify that the aircraft meets its design specifications
Okay.
and can perform its intended missions effectively.
And all of this data gets fed back into the design process.
It does. It's a continuous cycle of improvement.
Now, you mentioned a term earlier, aeroelasticity.
Yeah.
That sounds pretty complicated.
It can be, but it's a fascinating area.
So what is it in a nutshell?
Aeroelasticity studies the interaction between aerodynamic forces, inertial forces, and the flexibility of the aircraft's structure.
Okay, so like how the aircraft bends and twists in response to the forces it experiences during flight.
Exactly.
Why is that so important?
Well, those interactions can lead to some interesting phenomena.
Okay.
One example is flutter.
Flutter, what's that?
Flutter is a type of vibration that can occur when aerodynamic forces interact with the natural frequencies of the aircraft's structure.
Okay.
If it's not addressed, flutter can quickly escalate and lead to catastrophic structural failure.
That sounds bad.
It is. That's why we test for it.
So how do they do that? Test for flutter.
Engineers use specialized instrumentation to measure the vibrations and deflections of the aircraft's structure
Right.
at different speeds and altitudes.
So they're looking for any signs of unusual vibrations
Exactly. If they detect anything suspicious, they investigate further.
to make sure it's not a sign of a bigger problem.
Right.
Okay, let's talk about avionics for a minute.
Okay.
All those electronic systems on board.
The brains of the aircraft.
Exactly. What kind of testing do they do for those?
Avionics testing is critical. We need to make sure all those systems work flawlessly, both individually and together as an integrated system.
So like navigation, communication, flight control.
All of that and more.
How do they test all of that?
They use a variety of techniques.
Okay.
Ground-based simulations, laboratory tests, and in-flight evaluations.
So they're really putting those systems through their paces.
They are.
Okay, we've talked a lot about the technical side of things, but what about the people behind all of this?
The engineers.
Yeah. What kind of people are drawn to aerospace engineering?
Well, aerospace engineering attracts a diverse group of individuals,
Okay.
but they tend to share a few key traits.
Like what?
First and foremost, they have a passion for flight and a genuine curiosity about how things work.
So they're like the dreamers and the explorers.
Exactly. But it takes more than just passion to succeed in this field.
What else?
You need a strong foundation in science and mathematics.
Right, all those complex calculations.
Exactly. But beyond technical skills, you also need creativity and innovation.
Okay, so you need to be able to think outside the box.
You do. Aerospace engineers are constantly pushing the boundaries of technology.
Right.
So you need to be able to think critically, solve problems creatively, and adapt to new challenges.
What about teamwork and communication skills? Are those important too?
Absolutely. Aerospace engineering is a highly collaborative field.
Okay.
Engineers work together in teams to design, build, and test these complex systems.
So being able to communicate effectively is essential.
It is.
So the best aerospace engineers are like a blend of technical brilliance, creative problem solving, and strong interpersonal skills.
That's a great way to put it.
What advice would you give to someone who's interested in pursuing a career in this field?
I'd say follow your passion and explore all the different facets of aerospace engineering.
Okay.
There are so many paths you can take.
Right.
From designing aircraft structures to developing propulsion systems to working on cutting-edge space exploration missions.
So there's something for everyone.
There is. Reach out to people in the field, get involved in clubs and projects, and never stop learning.
That's great advice. It sounds like a field with endless possibilities.
It is. And the future of aerospace engineering is incredibly exciting, with advancements in areas like electric propulsion, hypersonic flight, and autonomous aircraft on the horizon.
Speaking of the future, what are some of the big challenges and opportunities that lie ahead?
One of the biggest challenges we face is the need to make aviation more sustainable.
Okay, with climate change and all that.
Exactly. The industry is under pressure to reduce its environmental impact.
So how is aerospace engineering addressing that?
There's a lot of research and development happening in areas like electric propulsion,
Okay.
which could significantly reduce emissions.
Electric planes, that'd be amazing.
It would. And we're also seeing advancements in sustainable aviation fuels made from renewable sources.
So it's like a multi-pronged approach.
It is. We're looking at both new technologies and alternative fuels.
What about space exploration? What's on the horizon there?
Space exploration is entering a new golden age. We're seeing a resurgence of interest in lunar exploration,
Okay.
with plans to establish a permanent human presence on the moon.
Wow, that's exciting.
It is. And Mars remains a tantalizing target.
Right, eventually getting humans to Mars.
Exactly. Robotic missions are paving the way for future human exploration.
So it's an exciting time to be following space exploration.
It is.
What about other exciting frontiers? Are there any other areas that you're particularly excited about?
Oh, there are so many. We're developing new materials that are stronger, lighter, and more resistant to extreme environments.
Oh.
We're designing hypersonic vehicles.
Like super fast planes.
Exactly. They could revolutionize travel and space access.
Wow, that would be incredible.
It would. And we're pushing the boundaries of autonomous flight with drones and self-flying aircraft.
Okay, so basically the future is looking pretty bright for aerospace engineering.
It is. It's a field that's constantly evolving and pushing the limits of what's possible.
It's been an incredible journey so far, exploring all these different aspects of aerospace engineering.
It has.
All right, welcome back to the Deep Dive. We've covered a ton of ground so far, from the history of aerospace engineering to the mind-blowing science behind how things actually fly.
And we've talked about some of those groundbreaking aircraft and spacecraft that have really pushed the limits.
We have.
Yeah.
But there's one piece of the puzzle we haven't really talked about yet.
Okay, what's that?
How does an aircraft actually get the okay to carry passengers? Like, after all the design and engineering and all that rigorous testing, how does it actually get, like, certified as safe?
That's where aircraft certification comes in.
Ah.
It's a crucial process that ensures every aircraft meets stringent safety and performance standards.
So it's kind of like a final exam for the aircraft, making sure it's ready for the real world.
Exactly. Think of it as the ultimate seal of approval.
From who? Who does the certifying?
In the United States, it's the Federal Aviation Administration, or FAA.
Okay, the FAA, I've heard of them.
They have a very thorough process that involves reviewing every aspect of the aircraft.
So it's not just about making sure the plane can fly. It's about making sure every detail meets the highest safety standards.
Precisely. The FAA scrutinizes everything, evaluating the strength of the structure, the reliability of the engines, the functionality of the avionics systems.
So they're leaving no stone unturned.
Exactly.
Okay, so walk me through this process.
All right, it usually starts with the manufacturer submitting a detailed application to the FAA,
What?
outlining the aircraft's design, specs, and intended use.
Like a massive report card.
Uh-huh, yeah, you could say that. And then the FAA reviews this application with a fine-tooth comb, examining every aspect of the design and proposed manufacturing processes.
So it's like presenting your masterpiece to the toughest critics in the world.
That's a great way to put it. And if the FAA is satisfied, they'll issue a type certificate.
What does that mean?
That means the aircraft's design meets their stringent safety standards.
Okay, so that's a big hurdle cleared. Is that the end of the process?
Not quite. Once the design is certified, the manufacturer needs to prove that each individual aircraft built actually matches that certified design.
Okay, so it's not enough to just have a good design on paper. They have to show that every plane they build actually lives up to those standards.
Exactly. It's like quality control on a massive scale.
So they're making sure every plane rolling off the assembly line is identical to the one that got certified.
Precisely. The FAA has inspectors who oversee the entire manufacturing process.
Wow, so they're really involved every step of the way.
They are. They check everything, from the materials used to the way those materials are assembled.
It's pretty amazing to think about all the checks and balances that are in place to ensure safety in aviation.
It is. It's a testament to how seriously the industry takes safety.
Okay, so we've talked about how planes get certified, but what about spacecraft? How does that work?
Spacecraft certification is a bit different.
How so?
Well, for one thing, the environment of space is far more extreme than the atmosphere.
Right, all that radiation and micrometeoroids and stuff.
Exactly. So, spacecraft certification needs to ensure the spacecraft and all its systems can handle those rigors.
I see. So is there, like, a space FAA?
It varies depending on the country and the mission. In the U.S., NASA has its own internal process for certifying spacecraft.
Makes sense. They're the ones launching most of the stuff anyway.
Right, they have very rigorous safety and mission assurance programs.
What about international collaborations?
Yeah.
Like when multiple countries are working together on a mission?
That's where things get really interesting. International collaborations often involve working together to create shared certification standards.
Oh, wow. So they have to agree on what's safe.
They do. The different space agencies involved will collaborate to define safety protocols.
So it's like a global team effort, making sure space exploration is done safely and responsibly.
Exactly. That kind of international cooperation is crucial for advancing our understanding of the universe.
You know, we spent a lot of time talking about the technical aspects of aerospace engineering.
Yeah, it's a fascinating subject.
It is, but I'd love to hear your thoughts on the broader impact of this field.
Okay.
Like, how has aerospace engineering shaped our world, our everyday lives?
It's had a truly transformative impact. Think about air travel. It's revolutionized transportation, shrinking the world and connecting people across vast distances.
It's hard to imagine a world without airplanes now.
It is. And then there's space exploration, which has pushed technological boundaries.
Right, and inspired generations to dream big.
Exactly. And it's led to countless advancements that benefit us here on Earth.
Like what? Give me some examples.
Satellite communication, GPS navigation, new materials, medical technologies.
It's amazing how the quest to explore space has had such a ripple effect on so many aspects of our lives.
It is. It's a testament to human curiosity and our desire to push the boundaries of what we know.
That's a great point. So as we wrap up this incredible deep dive,
Yeah?
what are your thoughts on the future of aerospace engineering? What's next?
Oh, the future's full of possibilities. One area that's particularly exciting is electric propulsion.
Oh yeah, electric planes and rockets.
Exactly. Imagine a world with quieter, more efficient, and more environmentally friendly aircraft.
That would be amazing. But what are the challenges there?
Battery technology is a big one. We need batteries that are lightweight, have high energy density, and can handle the demands of flight.
Okay, so it's a work in progress.
It is, but there's a lot of promising research happening.
What about hypersonic flight? That seems like something straight out of science fiction.
Uh-huh. It does, doesn't it? But it's becoming a reality. We're talking about speeds greater than Mach 5.
Wow, that's like really fast.
It is. And it has the potential to revolutionize travel and space access.
Okay, but what are the challenges with that?
The extreme speeds and temperatures create all sorts of engineering challenges. We need new materials that can withstand the heat
Right.
and propulsion systems that can generate enough thrust to achieve those speeds.
So, a lot of technical hurdles to overcome.
There are, but the potential is huge.
What about autonomous aircraft? Where do you see that technology going?
Autonomous aircraft are already changing the game in many industries, from package delivery to agriculture.
Yeah, drones are everywhere these days.
They are, and as the technology matures, we'll see even more applications emerge.
But with more autonomous aircraft in the skies, doesn't that raise concerns about safety?
It does, and safety is paramount. We need to develop robust systems to prevent accidents.
Okay, so there's a lot to figure out, but the potential benefits are huge.
They are.
Well, this has been an absolutely fascinating journey. I feel like I've learned so much about the past, present, and future of aerospace engineering.
It's been a pleasure sharing this depth dive with you.
The pleasure was all mine. Any final thoughts before we wrap up?
Aerospace engineering is a field that captures the imagination. It embodies the spirit of innovation and exploration.
It's about pushing the boundaries of human ingenuity and exploring the vast unknown.
Exactly.
Well said. And who knows, maybe some of our listeners today will be the ones shaping the future of aerospace engineering.
That would be amazing.
Yeah, designing those next-generation aircraft and spacecraft that will take us to even greater heights. Thanks for joining us on The Deep Dive. We'll see you next time.